Today our lecture is preparation and properties of alcohols. So first I will write the topic here. Preparation and properties of alcohols. Alcohols are basically hydroxy derivatives of alkenes. Hydroxy derivatives of alkenes. So these are alcohols. Alkane, what is the general formula for alkane? RH. It is alkane minus hydrogen plus OH. It results in the formation of ROH. So RO is the general formula for the alcohol. This R can be alkyl or aryl. Sorry, this can be alkyl but not aryl. So there are types of alcohols. Monohydric alcohols, containing one OH group. So the alcohols which contain only one OH group are known as monohydric alcohols. Second, dihydric alcohols containing two OH groups. The alcohols which contain two OH groups are known as dihydric alcohols. Third, trihydric alcohols. Alcohols containing three OH groups are known as trihydric alcohols. Dihydric and trihydric alcohols are known as polyhydric alcohols. These are collectively known as polyhydric alcohols. So these monohydric alcohols, this is our syllabus part, so we will be discussing this monohydric alcohols in detail. Monohydric alcohols, it is the target, so we have to discuss these monohydric alcohols completely. They are monohydric alcohols, the alcohols which contain only one OH group, are known as monohydric alcohols. So far monohydric alcohols are concerned, they can be classified into three categories: primary alcohols, secondary alcohols, and tertiary alcohols. So classification of monohydric alcohols. Classification of monohydric alcohols, that is our concern. Classification of monohydric alcohols. Number one, primary alcohol. This carbon is attached to one carbon, so this is primary alcohol. Secondary alcohol, when this central carbon is attached to two other neighboring carbons, that is secondary alcohol. And tertiary alcohol, that is this carbon is attached to three other carbon atoms, it's known as tertiary alcohol. So one more, this is methyl alcohol. In certain books it is written as 0 degree alcohol, but it is read as methyl alcohol. So there are certain conditions for a compound to be alcohol. Necessary conditions. So what are the conditions for a compound to be alcohol? That is number one. Conditions. In alcohol, OH must be attached to sp3 hybridized carbon. So this is the first condition for a compound to be alcohol. OH must be attached to the carbon which is sp3 hybridized. That is the carbon in which valency is satisfied by single bonds. If the OH group is not attached to sp3 hybrid carbon, say sp2 hybrid carbon, it is attached to carbon-carbon double bond, that is sp2 hybridized carbon. What happens? Let us see. So if it is attached to CH3COH double bond CH2. So here OH, it is attached to the carbon which is sp2 hybridized, and here it is sp3 hybridized. So what happens? It tautomerizes. Tautomerization. This hydrogen will migrate to this methylene unit, that is CH3. It becomes CO and CH3. So this is ene and all. This is enol form, and this is the keto form. It is 99.97%. It is 0.03%. So keto form is highly stable. Why this is highly stable? So far this carbon-carbon double bond is concerned, bond energy of carbon-carbon double bond, it is 256 kilojoules per mole. So for carbonyl group, it is carbon double bond oxygen, it is strength, that is bond energy, it is 364 kilojoules per mole. So this bond is stronger than this carbon-carbon double bond by about 110 kilojoules per mole. It's more stronger bond. So that is why this bond is formed at the cost of breaking up this bond, at the cost of this bond, double bond. So this form is more stable. So this is the necessary condition. Another condition for compound to be alcohol, that is another condition, that is not more than one OH group must be attached to a carbon. Not more than one OH groups must be attached to a carbon. Not more than one OH groups must be attached to a carbon. So that is, otherwise elimination takes place and there is formation of carbonyl compounds. If a compound has more than one OH groups attached to a carbon, so there is elimination, that is elimination takes place, elimination of water. The compound is unstable and there is formation of carbonyl compounds. Because these two OH groups, when they are attached to a carbon, they have good eliminating properties. There is a tremendous eliminating property. There is loss of water because this compound is unstable. So there is loss of water and it results in the formation of carbonyl compound. So what are the two conditions for a compound to be alcohol? Number one, not more than one OH groups must be attached to a carbon, and another, OH must be attached to sp3 hybridized carbon. So number one condition, I repeat again, OH must be attached to sp3 hybridized carbon, and here another, that not more than 2 OH groups must be attached to a carbon. Now let us discuss the preparation part of alcohols. Preparation. So for oxidation number of carbon in organic compounds is concerned, oxidation number of carbon in organic compounds, it is lowest in alkenes, more in alkenes, more in alkynes, then alkyl halides, then equal to alcohols, then aldehydes and ketones, and then carboxylic acids and derivatives. So our target is this alcohol. If I want to prepare this alcohol, I can prepare it from alkenes. Alkene I can prepare it from alkenes, but not from alkynes. Alkenes, they have lesser oxidation number of carbon. So carbon is having lesser oxidation number than carbon in case of alcohols. So if I want to shift from alkanes to alcohols or alkenes to alcohols, I have to increase the oxidation number of carbon. So that is oxidation. I have to do oxidation. So if I will prepare it from aldehydes and ketones or from carboxylic acids to carboxylic acids, and then I have to do reduction. So because I am decreasing the oxidation number of carbon. Then if I want to prepare it from the alkyl halides, so oxidation number of carbon here in both the cases is same, so I will go for substitution. I will prepare alcohols from alkenes. I will prepare alcohols from alkenes. I have to go for oxidation. If I will prepare the same from aldehydes and ketones and carboxylic acid and their derivatives, then I have to do reduction. So if I will prepare it from alkyl halides, then I have to go for the substitution. So alkanes by from alkenes, alcohols are not prepared. Now preparation from number one from alkenes. Alkenes are generally, so what I have to do? Oxidation. Alkenes are generally resistant to oxidation, so they do not undergo oxidation. However, if carbon is tertiary, in case of alkenes, then they undergo chemical oxidation with KMnO4 and they result in the formation of alcohol. Net result is the insertion of oxygen between carbon-hydrogen bond. So this from alkenes. Alkenes are generally resistant to oxidation. However, alkenes with tertiary carbon can undergo chemical oxidation with KMnO4 potassium permanganate, because potassium permanganate, it is the oxidizing agent, because here manganese is in +7 oxidation state, so it can never exceed its oxidation number than 7, because only 7 valence electrons are present in manganese. So far this oxidation is concerned, so this is a chemical oxidation because we are using KMnO4 as an oxidizing agent. CH3, CH2, OH, KMnO4, no reaction. Just I told you, because these are resistant to chemical oxidation, so there is no reaction. If alkane having tertiary carbon like this, then it undergoes oxidation with KMnO4. So what is the result? There is insertion of oxygen between carbon-hydrogen bond. Between carbon hydrogen bond. So there is insertion of oxygen, so there is formation of tertiary alcohol. Only tertiary alcohols can be prepared by this oxidation method when we are oxidizing, when we are using KMnO4 as an oxidizing agent. So it can oxidize only alkanes having tertiary carbon to alcohols, and net result is, so I will here write the result. Result is insertion of oxygen in CH bond. So this is the result of this reaction. So this was the preparation of alcohols from alkenes. No other method can be used, because only one, I will repeat, only one method, that is this chemical oxidation. By chemical oxidation you can convert only those alkenes into alcohols which are having tertiary carbon, and the compound, the alkene with tertiary carbon can be oxidized to tertiary alcohol by KMnO4. Then we have got alkenes. Then preparation of alcohols from alkenes. So far alkenes are concerned, we have three methods. One is hydration, another is oxymercuration, demercuration, and third is hydroboration. Number one. So from alkenes, hydration, alcohols. Oxymercuration, demercuration, alcohols. Hydroboration, and result is again alcohols. So maybe nature of alcohols will be different. So far this alkene is concerned, we can prepare alcohols from alkenes by three methods. Number one is hydration, number second is oxymercuration, demercuration, and number third is hydroboration, oxidation. Now we will prepare it first by hydration. This is carbon-carbon double bond. These are the alkenes. Hydration, that is addition of water in presence of H2SO4. What will happen? So there is formation of alcohol. We will discuss also the mechanism part, but one thing is there. First I will tell you that this result is addition of water across carbon-carbon double bond. Mechanism. CH2 double bond, CH2 plus H2O. It gives CH3, CH2OH. So this is the general reaction and mechanism part. First, in presence of H positive. First is protonation, this dissociation of this H2SO4. It gives H positive plus HSO4 negative. Then CH2 double bond. So this is weak pi electron cloud, free pi electron, it will interact with this proton. So it forms cyclic transition state. So that means, analogy, this H positive gets trapped in this electron cloud. So what happens then? Then there is nucleophilic attack, but this step is slow. Then we have got water. It will act as a nucleophile and it will attack here. It forms CH3, CH2, OH2 positive. So this is the protonated alcohol, and in this protonated alcohol there is loss of proton and it results in the formation of alcohol. And this step is fast. So here in the slow step addition of electrophile takes place, and in fast step addition of nucleophile takes place. So we can call it as an electrophilic addition. The reaction is electrophilic addition. Electrophilic addition. No doubt there is addition of electrophile as well as nucleophile, but the slowest step, that is the rate determining step. So that is addition of this electrophile and this is the slow step. So we can call it as electrophilic addition reaction. Maybe there is an unsymmetrical double bond now. That is propene, CH3, CH double bond CH2 plus H2O in presence of H2SO4. It gives CH3, CHOH and CH3, but not CH3, CH2, CH2OH. So in this reaction, positive part is attached to the carbon which is carrying more number of hydrogen. That is simple. Positive part to hydrogen rich carbon. That is known as Markovnikov's rule. Markovnikov's rule. So this is Markovnikov's rule. So here Markovnikov's rule. This positive part here goes to the carbon carrying more number of hydrogen atoms. So mechanism. CH3, CH double bond CH2, H positive, which comes from H2SO4, cyclic transition state. So chances now here possibility of this, that two types of carbocations may form here. Number one, it is CH3, CH positive and CH3, and second it is CH3, CH2 and CH2 positive. So this is secondary carbocation, this is what? Primary carbocation. Secondary carbocation is more stable. So on this secondary carbocation, this nucleophile attacks. That is water. It will form CH3, CHOH2 charge positive and CH3. So there is what this proton loss and it forms CH3, CHOH and CH3. So secondary alcohol is formed. So according to Markovnikov's rule, this takes place via more stable carbocation formation. I can write here, reaction proceeds via more stable carbocation formation. Now I can cite one more example. If so first homework, CH3, CH3, CH double bond, CH2 plus H2O in presence of H2 or acidic and that's H2SO4. So what will be the product? That is your homework. This was about the preparation of alcohols from alkenes by hydration. Now very important method we are discussing. that is oxymercuration, demercuration. It's a very, very important topic. Oxymercuration, demercuration. CH3, CH double bond, CH2 plus H2O in presence of HgOCO CH3 whole to number 1 and number 2 sodium borohydride. There is secondary alcohol but not primary alcohol. So there is formation of secondary alcohol. Result is addition of water across carbon-carbon double bond according to Markovnikov's rule. But here I will write without rearrangement. Hint for the previous question which I gave you as homework, their rearrangement possibility is there. Their rearrangement will take place. That is known as the Wagner-Meerwin rearrangement. That is the hint for that question. So for this question is here, there is Markovnikov's rule, but there is no rearrangement in oxymercuration, demercuration. So first, now mechanism for the reaction. So mercuric acetate, HgOAC. I can simply write this acetate, OAC. It will dissociate as HgOAC positive plus OAC negative. That is acetate ion. This is the acetate ion. I can write it like this: CH3COO negative or simply OAC negative. It's one and the same thing. No difference at all. CH3CO negative. Now, this will act as an electrophile. We have got a carbon-carbon double bond here. CH3, CH double bond, CH2 plus HgOAC. This is positive. So interaction of this loose pi electron cloud will take place with this of Hg positive. So it results in the formation of CH3, CH, CH2. This is the three-membered cyclic transition state, OAC. This is charged positive. So cyclic transition state, three-centered cyclic transition state. What will happen? Here polarity will partial, this will be partial positive and this is partial positive. So what will happen? There is the secondary carbocationic nature and this is the primary carbocationic nature. Nature I can simply say is the nature CH3, CH, CH2, HgOAC positive. So water will attack here as it will form CH3, CHOH positive and this is CH2, it is HgOAC. So there is proton loss minus H positive. What will happen? CH3, CHOH and CH2, HgOAC. Now, this is treated with, this step is known as the mercuration because mercuration takes place. Now, if I will treat the same with NaBH4 sodium borohydride, it results in the formation of, CH3, CHOH and CH3. Reduction, that is addition of hydrogen. So this is tertiary alcohol. Secondary alcohol. So this removal of HgOAC, it is known as the demercuration. So this was mercuration and this step is demercuration. So it was mercuration and this is demercuration, oxymercuration and demercuration. There is no rearrangement. Why? Because there is no rearrangement. So once water attacks from this side and it is removed, the bond breaks. This cyclic transition state, this cyclic transition state which was unstable, and by attack of nucleophile, this bond breaks, and then finally when it is treated with sodium borohydrate and there is a release of HgOAc, and then addition of hydrogen takes place here and valency of carbon is completed. So in this fashion secondary alcohol is formed. So first step it was mercuration and this is demercuration. So there is no rearrangement. So this is addition, is the addition of this result of the reaction is addition of water across carbon carbon double bond without rearrangement. So this is the addition of, I can simply repeat, I will repeat once again, addition of water across carbon carbon double bond according to Markovnikov's rule, but without rearrangement. So this, if I will use this alcohol instead of water, then it is known as alkoxymercuration, demercuration. That time ethers are formed. I will here write, if ROH is used in place of water, then it is known as alkoxymercuration, demercuration, or CH double bond CH2 plus ROH, that is HgOAc whole to number 1, number 2, NaBH4. So again Markovnikov's rule, that is addition of ROH will take place. So it takes place as RCHOR and CH3. This is ether. So ethers are formed. This is known as the alkoxymercuration, demercuration. Now very important, that is addition of H and OH across carbon carbon double bond is anti-addition. So anti-addition takes place. The anti-addition reaction, that is the addition of water, that is H positive and OH negative, is anti to each other, that is, so this is OH and this is H. So this is known as the anti-addition. Now preparation of alcohols from alkenes by hydroboration. That I want to give you as homework. Preparation of alcohols by hydroboration. Then very important, very important, by oxidation methods. By oxidation methods. Number 1, from carbonyl compounds. Carbonyl compounds can be reduced to alcohols or COH, reducing agent. It gives RCHOH or CH2OH, and RCOR, this is reducing agent, and it gives RCHOHR. What the result? The result of the reaction is addition of hydrogen that comes from reducing agent across carbonyl group. So addition of H2 across CO group. carbonyl group. Reducing agents can be. Reducing agents are: number one, lithium aluminum hydride. It's a wonderful reducing agent. You can use, you will see this reducing agent we are using at number of places. Then we have got sodium borohydride, another important reducing agent, that is sodium borohydride. Number third, it is sodium oblique ethanol. Number four, it is aluminum isopropoxide. Number fifth, it is metal oblique acid. So metal can be iron, it can be zinc, and it can be tin. Acid can be HCl, it can be CH3COOH, and it can be H2SO4. So this is the fifth reducing agent. Then we have hydrogen oblique nickel, that is very important. Hydrogen oblique nickel, that is sixth, that is hydrogen oblique nickel. So this metal combinations, iron can be used with HCl, it can be used with acetic acid, it can be used with H2SO4. So three combinations. So it can be again used with these three, and this tin can also be used with this. So there are 6 plus 3, that is 9 and 9. So 9 with this, 9 with this. So 9, 2, 11, 13, 15, 17 and 19 reactions we can use. So these are the 19 reactions. So by using lithium aluminum hydride, sodium borohydride, sodium ethanol, aluminum isopropoxide, metal acid and hydrogen nickel, we can convert this carbonyl compounds into alcohols. So carbonyl compounds can be converted into alcohols by using these reducing agents. So what is the result? That is addition of water across carbonyl group. So now very important points you will note down. Number one, reduction by aluminum isopropoxide is known as MPV reduction. Number one, we will note these points. Number one, reduction by sodium oblique ethanol, aluminum isopropoxide. Aluminum isopropoxide is known as MPV reduction, Meerwin Pondrop-Verley reduction. So Meerwin Pondrop-Verley reduction. Then very important point, that is lithium aluminum hydride does not reduce carbon-carbon double bond. For example, CH2 double bond, CH single bond, CHO, lithium aluminum hydride, it is CH2 double bond, CH single bond, CH2OH. So carbonyl part is reduced but not carbon-carbon double bond. However, I will note here, however, if compound is alpha beta, if compound is beta aryl, alpha beta unsaturated carbonyl compound. However, if compound is beta aryl, alpha beta unsaturated carbonyl compound, then double bond is reduced. Now I will write here beta aryl, CH C6H5CH double bond, CH and CHO. So this is alpha carbon, this is beta carbon, beta aryl, alpha beta unsaturated. So alpha, this carbon attached to the functional group is known as alpha carbon, and this is beta carbon, so it is beta aryl, alpha beta, there is unsaturation, beta aryl, alpha beta, unsaturated carbonyl compound. If it is treated with lithium aluminum hydride, so it gives pH, that is C6H5 CH2 CH2 and CH2OH. So I will write here once again, C6H5 CH2 CH2 and CH2OH. So this is beta aryl alpha beta unsaturated carbonyl compound. In this case, both double bond as well as carbonyl part is reduced. Now, very important point, sodium borohydride doesn't reduce carbon-carbon double bond. So, reduce carbon-carbon double bond. So this sodium borohydride does not reduce carbon-carbon double bond. So I write here a reaction, that is CH2 double bond CH single bond CHO, hydrogen oblique nickel, here sodium borohydride, and here lithium aluminum hydride. So in this case, CH2 double bond CH single bond CH2OH is formed. In this case, CH2 double bond CH single bond CH2OH is formed. Here CH2 double CH3 CH2 and CH2OH is formed. So in this case, lithium aluminum hydride does not reduce carbon-carbon double bond. Sodium borohydride does not reduce carbon-carbon double bond, but hydrogen and nickel, that reduces both carbonyl part as well as carbon-carbon, this carbonyl part as well as carbon-carbon double bond. So very, very important points. So overall change in this reaction is conversion of carbonyl group into CH into, that is overall change. Overall change I will write here, overall change, CHO to CH2OH and CO to CHOH. Simple. This is very, very simple concept, that reduction here, it's addition of hydrogen across carbon-carbon double bond. Now, if I will write one more, that is reduction by benzaldehyde is also reduced by sodium ethanol, and that reduction takes place via coupling. So write down benzaldehyde PHCHO, benzaldehyde undergoes reduction with sodium ethanol via coupling, that is twice PHCHO, twice PHCHO, that is twice PHCHO Na C2H5OH, that is PHCHOH and CHOH and pH. So this is coupling. Couple means two, coupling. So mechanism, it is homework. So I will give you the mechanism of the reaction as homework. A reduction of by reduction of carboxylic acids. Alcohols can also be prepared by the reduction of carboxylic acids. So far carboxylic acids are concerned, that is RCOOH, that's RCOG, carboxylic acids and derivatives, I can say derivatives. RCOG, here it is reducing agent, it will form RCH2OH plus Hg. So far this carbonyl part is concerned, this carbonyl part is converted into the alcohol, and there is cleavage of carbon G bond. So what is G? G can be OH. G can be Cl, G can be OR. So if it is OH, then it is carboxylic acid. If it is Cl, if it is OR, then it is the derivative of carboxylic. It is acid chloride and this is acid, this is ester, and NH2, this is amide. So G can vary. G can be OH, then it is carboxylic acid. If G is Cl, it is acid chloride. If G is OR, it is ester. And if it is G is NH2, then it is acid amide. So what are the reducing agents? Reducing agents can be lithium aluminum hydride, and this simply lithium aluminum hydride. This lithium aluminum hydride is a very, very important reducing agent. So reducing agent, it is reducing agent is lithium aluminum hydride. For example, CH3, CH2, CO, OH in presence of lithium aluminum hydride. So it will result in the formation of CH3, CH2, CH2OH. So this is water. Here it is G and it is H. Hg, that is water plus water. Lithium aluminum hydride can reduce both acid part as well as ester part. Lithium aluminum hydride. Write down. Lithium aluminum hydride reduces both acid part as well as ester part. For example, this is ester and ester part. This is carbonyl part. This carbonyl part, it is lithium aluminum hydride. So what you will get? This is OH. This is OH, and this can be also OH. So there is, it reduces this ester part. This is the ester part. So ester part can be reduced by lithium aluminum hydride. If it is sodium borohydride, it reduces only carbonyl part but not ester part. So sodium borohydride cannot be used for this ester part. Simple, that is OH and this will OH. So this reduces only carbonyl part to alcohols but not ester part, and lithium aluminum hydride reduces both carbonyl part as well as ester part, or it will reduce also acid part of the compound. Now another important, that is reduction by BH3. Reduction by BH3 is very important reaction. Reduction by BH3. Reduction by BH3. BH3 can also be used as a reducing agent in presence of THF. So RCOOH, BH3 oblique DHF. It gives RCH2OH. So again there is formation of alcohols. Now say there is ester part as well as carbonyl, this ester part in the compound. So this BH3 is more effective towards the ester part, and if we are using lithium aluminum hydride, that is more effective towards ester part. Now very, very important point, note, if both acid part, acid as well as ester part is present in the compound, then BH3 is more reactive towards acid part, and lithium aluminum hydride towards ester part. For example, I have CH2 whole N This is COOH and this is COOR. Here it is lithium aluminum hydride and here it is BH3/BHF. As I have mentioned here, lithium aluminum hydride is more towards ester part, so the product will be, what will be the product here? It will be CH2, COOH, CH2 whole N and CH2OH. Here it will be CH2OH, CH2 whole N and COOR. So BH3 is more reactive towards ester part and lithium aluminum hydride is more reactive towards ester part. So this was about what? Reduction of esters and their derivatives. Now very important method, very important method that is preparation of alcohols. Preparation of alcohols by substitution method, that is from alkyl halides. So why I have not mentioned it? I should have mentioned that part before this. So preparation of alcohols from alkyl halides. It is already done. See preparation of alkyl. See chemical properties of alkyl halides. There I have mentioned this detail with mechanism. So for chemical properties are concerned, now chemical properties. We have different types of reaction in case of alcohols. Number one, chemical properties. Number one, reactions due to cleavage of OH bond. Number second, reactions due to cleavage of CO bond. Number third, oxidation. Number four, reduction. So chemical properties are concerned. So for chemical properties are concerned, we have different types of chemical properties. Number one is reaction due to cleavage of OH bond, reaction due to cleavage of CO bond, then we have got the oxidation, and then we have got the reduction. So for reactions due to the cleavage of OH bond are concerned, we will discuss them in detail. It indicates the acidic character of alcohols. Reactions due to cleavage of OH bond. By this reaction we can discuss the acidic character of alcohols. ROH, it dissociates as RO negative plus H positive. So release of this H positive indicates its acidic character. So Ka, RO negative, H positive divided by concentration of ROH. So Ka is directly proportional to acidic strength. Also Ka is directly proportional to stability of RO negative ion, that is acid anion. So Ka is inversely proportional to magnitude of charge on acid anion. So far Ka is concerned, higher the value of Ka, more will be the acidic strength. Higher the value of Ka, more will be the stability of acid anion. Higher the value of Ka, lesser will be the magnitude of charge, or higher the magnitude of charge, lesser will be the value of Ka. So simply we can, if I will combine the two, so Ka is directly proportional to the stability of acid anion. Ka, this stability of acid anion, is inversely proportional to what? Magnitude of charge. So with the help of this, I can discuss its acidic strength. Suppose I have CH3, CH2OH. I have CH3, CH3 and H, and this is OH. I have CH3, 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 OH, and we have HCOO, or simply CH3, COOH and HCOOH. 1, 2, 3, 4 and 5 acids. So if I will remove minus H positive, I will remove H positive, it will be HCOO negative ion. Here minus H positive, it will be C2H5O negative ion. Here it will be minus H positive, it will be CH3, CH3, it is H and it is O negative. Here minus H positive, it will be CH3, CH3, CH3 and O negative. So you can see the magnitude of charge. Here it is there is zero effect with this carbon hydrogen. Here it is plus I effect due to one methyl group. Here is plus I effect due to two methyl groups. Here is plus I effect due to three methyl groups. So definitely the magnitude of highest so if I will get highest magnitude of charge, and here it is lowest magnitude of charge. Highest magnitude of charge will be here. So if it's the highest is the magnitude of charge, lesser will be the value of Ka. If lesser will be the value of Ka, lesser will be the acidic strength. Highest magnitude of lowest magnitude of charge, highest value of Ka, and higher will be the acidic strength. So formic acid, this will be more stronger. So order of acidic strength, order of acidic strength, order of acidic strength. So 1 greater than, second greater than, 3 greater than 4. So this will be our greater than 5. So this will be the least stronger acid, and this will be weak acid, weakest acid, and this will be the strongest acid. So acid depends upon this acidic strength plus I effect. So higher the value of plus I power, higher the power of the plus I plus I effect, higher the value of K, greater will be the strength of acid, and more will be the plus I power. So plus I power is directly proportional. Plus I power is inversely proportional. Plus I power is inversely proportional to acidic strength. Acidic strength. So plus I effect has a very important effect on this acidic strength. Higher the value of Ka, higher will be the acidic strength. Higher, more will be the number of plus I groups, lesser will be the acidic strength. So this is very, very important now. Action now, number 1, action with metals. Action with metals. Action with metals. Number 1, ROH plus Ne. It gives RONE, sodium alkoxide, plus half of H2. Displacement of hydrogen gas from this compound by active metal indicates the acidic strength of the acidic character of the alcohol. So I will write here displacement of hydrogen gas by a metal from a compound indicates the acidic character of the compound. Now, for example, CH3, CH2, CH3, CH3H and OH. So this is 3 times plus aluminum. It gives CH3, CH3HO whole 3 Al. This is aluminum isopropoxide. Aluminum isopropoxide. We have discussed this. This is the reagent which is used in the MPV reduction. Reagent for MPV reduction. That is, by this reduction you are converting this carbonyl compounds into alcohols. MPV reduction. One more, CH3, OH 3 times plus aluminum. It gives CH3O whole 3 and aluminum. It is aluminum tertiary butoxide. So this aluminum tertiary butoxide, it is a reagent for open air oxidation. OPPNEAUER, open air oxidation. This is the reverse of the MPV reduction. So by this reaction you are converting alcohols into carbonyl compounds. This is known as the open air oxidation. So for this open air oxidation, what you are using, this aluminum tertiary butoxide is used. So this was action of alcohols with the metals. Now very important reaction, that is very important, that is esterification next. And that reaction also involves the cleavage of OH bond. That reaction also involves the cleavage of OH bond, that is MPV. This is that is the esterification. Esterification. Now it is preparation of esters by action of alcohols on carboxylic acids. In presence of H2SO4. RCOOH plus ROH. In presence of H2SO4, it gives RCOOR dash plus H2O. So there is formation of esters. The reaction is reversible, because hydrolysis, these esters can easily undergo hydrolysis with water to result in the formation of carboxylic acids and alcohols. So the reaction is reversible. So far this reversible nature is concerned, and it is due to the reactivity of high reactivity of these esters with that of water, and which result in the formation of carboxylic acids and alcohols. Reaction is reversible. In order to shift the equilibrium towards forward direction, one of the reactants is taken in excess, or water is removed as and when it is formed. So as and when the water is formed, we can remove it with the help of some apparatus known as the Dean-Stark apparatus. So this reacts with alcohol, that's carboxylate react with alcohol in presence of H2SO4, that results in the formation of ester. The esters can also react with water, they result in the formation of carboxylic acid and alcohols. So the reaction is reversible. In order to shift the equilibrium towards forward direction, one of the reactants is taken in excess or water is removed as and when it is formed. So far the size of alkyl group is concerned, it has a great this has a great relation with the reactivity. Size of R of carboxylic acid or alcohol is inversely proportional to reactivity because of the steric hindrance. Now mechanism, again I will give you mechanism as homework. We have done a lot of mechanism in the class. A lot of them show this mechanism homework. It's very simple. So here, hint, here bond of OH takes place, cleavage of OH bond takes place here. This is the hint. Here ROH undergoes oxygen hydrogen bond cleavage, not carbon oxygen bond cleavage. This is the hint for the reaction. This is the esterification. Now this is a very important reaction. This may be asked in the examination. Now reactions due to cleavage of OH bond. Reactions due to cleavage of OH bond. Reaction condition, that is temperature. In this case, higher temperature favors elimination and lower temperature favors substitution. Dehydration. There are two types of dehydration. Number one, it is intermolecular dehydration. So that is intramolecular dehydration. Intramolecular dehydration is the dehydration which takes place within the same molecule. Intramolecular dehydration. So by this reaction, alkenes are formed. For example, H2SO4, 473 Kelvin, or higher temperature, simply higher temperature, it is alkene. Now example and then mechanism. For example, CH3, CH, H, CH2OH, H positive, it gives CH3, CH double bond, CH2. Alkenes are formed. This is CH here. So formation of alkene, H in presence of H2SO4. Now I will discuss the mechanism of this reaction. Mechanism. Number one, first step is dissociation of H2SO4. So once H2SO4 it is dissociated, it results in the formation of H positive and HSO4 negative as per the requirement. So then second is protonation of alcohol. 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 CH3, CH2, CH2OH. Protonation. It results in the formation of protonated alcohol. Protonated alcohol. Protonated alcohol. So, third step is water loss. CH3, CH2, CH2 and OH2 positive. So this is water loss minus H2O. It gives CH3, CH2 and CH2 positive. This is the primary carbocation. This primary carbocation undergoes rearrangement, hydride shift, which is also known as 1,2 shift, which is also known as the Wagner-Meerwin rearrangement. That is, hydride will get shifted from carbon number 2 to 1, that is CH3, CH positive and CH3. This is the secondary carbocation. So secondary carbocation is more stable than the primary carbocation. And last step, that is the proton loss. Proton loss. So this is the primary and characteristic reaction of this carbocation, proton loss. By losing a proton, it results in the formation of CH2H. By losing this proton, it will get converted into CH3CH double bond CH2. So this is the alkene. So by this reaction, alkenes are formed. So this is intramolecular dehydration, that is dehydration within the same molecule. Now, number of examples can be cited on this type of dehydration. For example, I will give you an important example here. That is CH2 and COH2 and OH. H2SO4. It gives how? OH, H positive, it is protonated. It will form protonated alcohol. OH2 positive. Here it is water loss. It gets converted into, this is a primary carbocation. 1,2 shift, it gets converted into secondary carbocation. Again 1,2 shift, it gets converted into the tertiary carbocation, and then there is proton loss. There are two possibilities of proton loss. It can get released, proton can be lost from this carbon and it can be lost from this or this, it is one and the same. So by losing a proton, it will get lost from this carbon. Why? Because here carbon double bond 2 and 3, so 7 alpha hydrogens. If it is lost from this carbon, it will form this only 6 alpha hydrogens. Number of alpha hydrogens directly proportional to the stability of alkene. So this will be the product but not this, or this will be the minor product, or this can be the major product, because always we are taking major products into consideration. Another example can be given on this. For example, CH2OH. It is formed, cyclohexene is formed. So in this case, 5-membered ring has got converted into 6-membered ring by ring, it's known as the ring expansion, via ring expansion. Ring expansion. Mechanism: CH2OH, H positive, it is protonated alcohol, minus water, it gets converted into CH2 positive. So we have got 5-membered ring. It is more under strain more than 6-membered ring. So ring expansion. This CH2 unit gets converted. This is out of the ring and it comes in the ring. So as cyclohexyl carbocation, and this cyclohexyl carbocation loses a proton and it forms cyclohexene. So cyclohexene is the product for it. So this is again intramolecular dehydration. So by intramolecular dehydration there is formation of alkenes. Now intermolecular dehydration. Intermolecular dehydration. So for intermolecular dehydration is concerned, there the dehydration takes place between the two molecules. So by this method ethers are formed. For example, ROH plus ROH in presence of H2SO4 but lower temperature. So substitution takes place. It is ROR, this is ethers. Now mechanism. Example and then mechanism. CH3, CH2, OH twice in presence of H positive. So it gives ETOET, that is ethyl. So C2H5, this is C2H5, it is ethyl and ethyl. So mechanism of this reaction. Now mechanism of the reaction. CH3, CH2, OH, twice H positive, CH3, CH2, O, CH2 and CH3. Now this is the general reaction. I will give the mechanism. Number one step, protonation of alcohol, that is there. And first we have got two. So one alcohol, CH3, CH2, it gets protonated by H positive. So it results in the formation of CH3, CH2, OH2, and then there is water loss. CH3, CH2, OH2 positive, there is elimination of water, it forms CH3 and CH2 positive carbocation. We have one more alcohol, this CH3, CH2 positive, that acts as a nucleophile and that will attack on this carbocation CH2 and CH3. It forms a protonated ether, CH3, CH2OH and CH2 and CH3. This is protonated ether. This is unstable. So what this will do? It loses this proton, so it forms CH3, CH2O and CH2 and CH3. So this is the substitution is intermolecular dehydration. By this intermolecular dehydration, ethers are formed. So this was about the dehydration, and these dehydration comes under the title of that cleavage of carbon-oxygen bond. So it's all. So action of halogen acids with alcohols. Action of HX with alcohols. Alcohols, when treated with HX, here conditions, it is R X plus H2O. For example, CH3, CH2OH plus HCl in presence of anhydrous zinc chloride and heat, it results in the formation of CH3, CH2, Cl plus H2O. equimolar mixture of HCl and anhydrous zinc chloride is known as Leucos reagent. By this method only alkyl chlorides are prepared. Why? Because anhydrous zinc bromide is not stable. So by this method only RCl is prepared. And this method of preparation of alkyl halides is known as Grove's process. It is known as Grove's process. So far the mechanism of these reactions is concerned, it is done already. We have already done this when we discussed the preparation of alkyl halides. If I will prepare alkyl bromides from alcohols, then what I have to do? ROH plus HBr in presence of H2SO4. So H2SO4 is another dehydrating agent, that is RBr plus H2O. So here we cannot use zinc bromide. Why? Because zinc bromide is not a dehydrating agent, it is only anhydrous zinc chloride. So ROH plus HBr, it results in the formation of RBr. So in presence of H2SO4, also ROH plus HI, it results in the formation of, it is 57%. So it also results in the formation of alkyl iodide. In this reaction, that will be the homework today. If I will give you secondary alcohol plus HCl in presence of anhydrous zinc chloride and tertiary alcohol HCl, no need of anhydrous zinc chloride here, it will result in the formation of secondary alkyl halide. Here it results in the formation of tertiary alkyl halide. We need here anhydrous zinc chloride. We don't need here anhydrous zinc chloride. We need here anhydrous zinc chloride as well as heat. So that means this tertiary alcohol is more reactive than the secondary, and secondary is more reactive to the tertiary, this primary. So order of reactivity of alcohols is tertiary, secondary and primary. So mechanism of these reactions is already done when we discussed alkyl halides. So very important reaction, wonderful reaction, that is wonderful method of the preparation of alkyl halides, that is action of alcohols with thionyl chloride. Action of alcohol with thionyl chloride. The mechanism of that reaction is also done. ROH plus SOCl2, it gives RCl plus SO2 plus HCl. This is alkyl chloride. Again, by this method only alkyl chlorides are prepared. So this is the best method for the preparation of alkyl chlorides. Best method for the preparation of alkyl chlorides. Why? So SO2 it is a gas, HCl is a gas, both of them will escape and they will leave pure RCl behind, which needs no purification, because both of the gases will escape and they will leave pure RCl behind. Same ROH, again with PCl5, it results in the formation of RCl plus POCl3 plus HCl. Again, this reaction is also done when we discussed the preparation of alkyl halide. So this is the preparation of alkyl halide. All these reactions we have already done this. So very important. Now the best and most important method, most important reactions of the alcohols, these are the oxidation. So that is the main concern. That's the more and more important, most important reaction I can say of alcohols, that is the oxidation of alcohols, and that is our main concern. So oxidation. Before this, we discussed action of alkyl halides, action of alcohols with halogen acids, thionyl chloride, PCl5. So those reactions already we have discussed, and that was simple repetition of, we didn't discuss them in detail. So our main and prime concern is the oxidation of alcohols, and I will give you the simplest possible technique for this oxidation. Alcohol, RCH2OH, it gives RCOH, and R2, or simply RCH, R and OH, it gives RCOR. As I have told you, oxidation number of alcohol is of carbon is lesser than that of aldehydes and ketones. So if I will oxidize alcohols, they can easily be oxidized. They can easily be oxidized to aldehydes and ketones, because we are increasing the oxidation number. So also, if this is alcohol, oxidation number of alcohol, then oxidation number of aldehyde and ketone, then oxidation number of carbon in case of carboxylic acids. So it is lesser in alcohol, higher in aldehyde, highest in the carboxylic acid. If I will convert alcohols into aldehydes and ketones, I need the mild oxidizing agent, and if I will convert this into carboxylic acids, I need strong oxidizing agents. So if I will oxidize alcohols into aldehydes, ketones, so we need the mild oxidizing agent. Mild oxidizing agent. Simple, I will write here again. ROH and aldehyde, RCHO and RCOR. So these are alcohols and this is carboxylic. These are aldehydes and ketones and these are carboxylic acids. If I will convert alcohol into aldehydes and ketones, that is carbonyl compounds, I need mild oxidizing agent. And if I will convert alcohols into carboxylic acid, I need strong oxidizing agent. So first I will tell you about the mild oxidation. So I need here mild oxidizing agent. Here I need mild oxidizing agent. I will repeat once again. So far alcohols are concerned, the oxidation of alcohols, of carbon in case of alcohol is lower than that of aldehydes and ketones, and it is lower than that of carboxylic acids. If I will convert alcohols into aldehydes and ketones, I have to use mild oxidizing agent. If I will convert alcohols into carboxylic acids, I need strong oxidizing agents. So oxidation, that is alcohols into aldehydes and ketones, that is mild oxidizing agent. So by mild oxidizing agents, I will write here by using mild oxidizing agents, alcohols can be converted into carbonyl compounds. So that is aldehydes and ketones. I will write here RCH2OH, mild oxidizing agent. It gives RCHO, RCHOH and R. Mild oxidizing agent, it gives RCOR. So this is aldehyde and this is ketone. So primary alcohol can be converted into aldehydes and secondary alcohol can be converted into ketones. So far mild oxidizing agent is concerned. Now by mild oxidation, what are number one, which mild oxidant you can use? Number one, it is X2, that's halogen. Second, it can be KMNO4, OH negative. Third, KMNO4, H positive. Fourth, K2Cr2O7, H positive and heat. Number fifth, MnO2 oblique CH2 Cl2, it is fifth. Sixth, it is Sarret reagent, SARRET, Sarret reagent. and serrate reagent is CrO3 oblique pyridine, that is pyridinium chlorochromate. We can simply say PCC. And then we have seventh Jones reagent. That Jones reagent is CrO3 oblique dilute H2SO4. And Pentone's reagent. Next, that is eighth Pentone's reagent. That's Pentone's reagent. It is FeSO4 oblique H2O2. And we have very important, that is ninth we have that is copper oblique 300 degrees centigrade, and 10th we have silver oblique 300 degrees centigrade. So these are, by using these 10 reagents, do the 10 reactions, or 10 plus 10, these are the 20 reactions. So we can finish the 20 reactions within a small period, within a couple of minutes we can finish the 20 reactions. So these reagents, these are the oxidizing agents. These are the mild oxidizing agents. Mild oxidizing agents can convert these alcohols into, but not this. Sorry, I will KMnO4, it's a strong oxidizing agent. This cannot be used. So I am very sorry. So this not heat. So it is X2, it is K2Cr2O7 oblique H positive, and it is MnO2 oblique CH2Cl2. It is serrate reagent, it is Jones reagent, it is Pentone's reagent, and it is hot copper and hot silver. But not, I repeat again and again, I repeat once again, but not KMnO4. Why I will write here, KMnO4 is a strong oxidizing agent. Sorry, again, strong oxidizing agent. So it's not used because it's strong oxidizing agent. So KMnO4, so again I will repeat once again, by using mild oxidizing agents, alcohols can be converted into carboxylic carbonyl compounds. So the mild oxidizing agents are X2, K2Cr2O7 H positive, MnO2 CH2Cl2, serrate reagent, Jones reagent, Pentone's reagent, hot copper and hot silver. So these are very, very important mild oxidizing agents by which you can convert primary alcohols into aldehydes and secondary alcohols into ketones. It's a very, very important reaction. Now, oxidation by strong oxidizing agents. This will be your homework. Now, miscellaneous oxidations. Number one, oxidation by O2 oblique platinum. By this method, by this oxidation, primary alcohols are converted into carboxylic acids. For example, CH2OH, CHOH, whole 4 and CH2COOH. O2 oblique platinum, so it is COOH, CH2, CHOH, whole 4 and COOH. So this is the primary alcoholic group. This can be converted into carboxylic acids. And another oxidizing agent, that is oxidation by X2 oblique OH negative. This oxidizing agent is used for only those compounds those alcohols which are having a beta methyl group. The oxidizing agent is used for the alcohols. The oxidizing agent is used for the alcohols which have beta methyl group. It involves carbon-carbon bond cleavage between carbonyl carbon and carbon of beta methyl group. In this reaction, beta CH3 is converted into CHX3 and carbonyl part into carboxylic acid. For example, CH3, CH2, COCH3, X2 oblique OH negative. This part into carboxylic acid, as I have mentioned above, COOH plus CHX3. If X2 is iodine, then CHI3, that is iodoform, is formed. Iodoform, that is yellow precipitate. So by this oxidizing agent, there is involvement of the carbon-carbon bond cleavage between carbonyl carbon and beta methyl carbon, and carbonyl part is converted into carboxylic acid and CH3 into CHX3. If X is I2, then CHI3 is formed, which is iodoform, and that is yellow precipitate, that is iodoform test. Simple, one more example I can give. In presence of X2 oblique OH negative and plus CHX3. This is hollow form. This is very, very important oxidation. Now reduction. Alcohols can be reduced to alkenes. Reduction. Alcohols can be reduced to alkenes. Simple reaction. Result is removal of oxygen. R OH HI oblique P or lithium aluminum hydride oblique tosyl chloride TSCl. What is the result? Removal of oxygen, it is formation of alkane. So both reagents can be used, HI oblique P or lithium aluminum hydride and tosyl chloride, that is ROH can be converted to RH. So result is the removal of OH. So this OH is, removal of oxygen, that O is removed and there is direct carbon hydrogen bond formation, and carbon simply I can say CO2 CH bond. So this is the result of the reduction. So this was all about the preparation and properties of alcohols. Now distinction between primary, secondary and tertiary alcohols. Now distinction between primary, secondary and tertiary alcohols. There are a number of methods by which you can differentiate primary, secondary and tertiary alcohols. Distinction between primary, secondary and tertiary alcohols. Number 1. By hot copper CH3 alcohol, copper oblique 300 degrees centigrade. If there is alkene, alcohol was tertiary alcohol. If there is formation of aldehyde, ketone, then it was secondary alcohol. And if it is formation of RCHO, it was the primary alcohol. So this is dehydrogenation and this is dehydration. Dehydrogen, these two reactions. So it was the secondary alcohol. So simple, I can say CH3, 2CH, CH3 and OH. By hot copper, dehydration takes place. So there is formation of alkene. If it is secondary alcohol, it is dehydrogenation. It is dehydrogenation. Copper oblique 300 degree, it is CH, H and so it is aldehyde. No, it is ketone. It is ketone. And if it is CH3, H and OH, copper 300 degrees centigrade, it is CH3COH. So from primary alcohols, aldehydes are formed. From secondary alcohols, ketones are formed. And from tertiary alcohols, alkenes are formed. So note, silver can also be used in place of copper. So we can distinguish primary, secondary and tertiary alcohols by hot copper as well as by hot silver. So another important method is by Leucos test. By Leucos test. By second Leucos test, rather third, hot silver and hot copper. Leucos test. Alcohol. Anhydrous zinc chloride and zinc chloride. Turbidity, that is cloudiness, appears at once. If turbidity appears at once, then alcohol was tertiary. If turbidity appears after a few minutes, turbidity appears after few minutes, secondary alcohol. Turbidity appears only upon heating, then it was primary alcohol. As I told you, if I take alcohol and I will treat it with anhydrous zinc chloride, if turbidity appears, cloudiness appears at once, then it is tertiary alcohol, and if it appears after a few minutes, then it is secondary alcohol. If it appears only upon heating, then it is primary alcohol. So this indicates the reactivity of tertiary alcohol is more than that of the secondary alcohol, and secondary alcohol is more than that of the primary alcohol. So this is known as the Leucos test. And Third and important test is known as the Victor-Meyer test. By Victor-Meyer test. By Victor-Meyer test. By Victor-Meyer test. Alcohol. Alcohol is treated with phosphorus in presence of iodine. Heat. Number one. Second, AgNO2. Number third, it is NaNO2 concentrated H2SO4, NaNO2 oblique H positive, and fourth OH negative. That is base. Red color, primary alcohol. Blue color, secondary alcohol. No color, tertiary alcohol. My dear students, I have discussed all the methods of distinction of primary, secondary and tertiary alcohols, but the reaction of Victor-Meyer test is your homework, and that's all for the preparation, properties and distinction of primary, secondary and tertiary alcohols. Preparation, properties of alcohols and distinction between primary, secondary and tertiary alcohols. That's all for the day.